This is the first lecture in the oscillatory motion topic. In this lecture, we're going to be looking at springs and simple harmonic motion. This lecture covers sections 15.1 and 15.2 of your textbook. First of all, a quick recap of last lecture. The most important points from last lecture were that we saw three different methods that heat could be transferred through. The first was conduction, and we saw that this obeyed the equation P, which is the Q over the time, is equal to Ka dt dx, where K is the thermal conductivity constant. We saw that this was the form on your formula sheet, but it was probably more useful to write it as P is equal to Ka dH minus Tc over L, where L is the thickness of our material. We then just quickly introduced R values, which you might come across if you go on in engineering. R values describe the thermal conductivity of different materials. We also had a quick look at convection and said the equations were too complicated, so they were beyond the scope of this course, but convection is another method of heat transfer, as is radiation. And the amount of heat transfer by radiation is given by the power, Q on T, is equal to sigma A E T to the 4, where sigma is Stefan's constant, A the surface area, E the emissivity, and T the temperature in kelvins. So the net rate of heat transfer it comes about because of the difference in the temperature to the power of 4, because things are always absorbing heat from the surroundings as well as releasing it. Okay, so on to a new topic. First of all, a definition of periodic motion. Periodic motion is the motion of an object that regularly returns to a given position after a fixed time interval. So a special type of periodic motion is simple harmonic motion. Sometimes it's written as SHM, so if you see SHM, it's talking about simple harmonic motion. This is a type of periodic motion where the force is proportional to the distance from the equilibrium position and directed towards the equilibrium position. So you came across Hooke's law earlier. It causes a spring to undergo simple harmonic motion. So when we start a spring bouncing, it continues to bounce with simple harmonic motion. These diagrams show you a spring undergoing simple harmonic motion. The further we pull it from its equilibrium position, the greater the force. The force is always pushing it back towards its equilibrium position. So if we pull it to the right, the force is to the left. If we pull it to the left, the force is to the right. And when it's at its equilibrium position, there is no force. Okay, so let's consider acceleration during simple harmonic motion. You know that acceleration is very closely related to force through Newton's second law. So the acceleration during simple harmonic motion is not constant. So you cannot apply the kinematic equations as they assume constant motion. However, we can use Hooke's law. So we know that F is equal to minus kx, and that's equal to m times a. So that tells us that the acceleration, in this case in the x direction, is equal to minus k on mx. Now, the maximum displacement we can have in simple harmonic motion is called the amplitude. So the maximum acceleration will occur when x is equal to the amplitude, so when x is plus or minus a. Okay, a question. A body oscillates with simple harmonic motion between x equals 2 and 10 meters. What is the amplitude of the motion? What is the equilibrium position? And what is the acceleration of the block at the equilibrium position? Okay, so we have our block. It's oscillating between 2.0 centimeters and 10.0 centimeters. Let's start off with what's the equilibrium position. Well, the equilibrium position is halfway between these two, so that is at 6.0 centimeters. This is the equilibrium. And we were asked what was the amplitude. Well, the amplitude is the maximum displacement from the equilibrium position, so you can see it's 4.0 centimeters up there. It would also be 4.0 centimeters to get down here. So the amplitude is equal to 4.0 centimeters. And then we were asked, when it's at its equilibrium position, what's its acceleration? Well, F is equal to minus kx is equal to ma. Since it's at equilibrium, its displacement from equilibrium is 0, so its acceleration is equal to 0 at the equilibrium position. Okay, so we just wrote down that the acceleration was equal to minus k on mx, and we know that acceleration is the second derivative with time of the displacement. So we need to come up with an expression that is going to satisfy this differential equation. An equation of the form xt is equal to a cos omega t plus phi will satisfy this. In a minute we'll prove this. Is this the only solution? Well, no, it's not. A sine function would also satisfy it. And then why do we bother to put in this phi? It's not needed to satisfy this equation, but it gives this equation a more general form. If we have this format, then we can satisfy any initial conditions, which isn't true if we don't have the phi. Okay, so now our task is to prove that x is equal to a cos omega t plus phi will satisfy ax is equal to minus k on mx. Okay, so we've got x is equal to a cos omega t plus phi. And we have to show d squared x dt squared, which is a of x, is equal to minus k over mx. That this satisfies this. Okay, let's take the first derivative of this function here. We know that the derivative of the position is equal to the velocity. So velocity is dx dt. Okay, to take the derivative of this, we've got a function of time in here. So when we take the derivative of a cos function, we end up with a minus sign. So we've got minus a, this constant. The derivative of the inside of this cos function is omega, and then sine omega t plus phi. Okay, now we need to take the second derivative of this function. So the acceleration is equal to d squared x dt squared, and this is equal to minus. Now when we take the derivative of sine function, we end up with cos. We also need to take the derivative of what's inside. So this is a omega squared cos omega t plus phi. Okay, now with this function, the a cos omega t plus phi, up here, that's what we called x. So we can write this as equal to minus omega squared x. And we were asked to show that this satisfied an equation of this form. So we need to show that this is equivalent to minus k on mx. Well, omega is just any number. We haven't defined what omega actually is yet. So it can be anything. And we've got this negative out the front, we've got this negative, we've got this x, and we've got this x. So these are of the same form as long as omega squared is equal to k on m. So this satisfies our simple harmonic motion requirements if omega is equal to the square root of k on m. So this equation actually appears on your formula sheet. This one you're expected to know. This slide's showing you the graphs for the position, the velocity, and the acceleration. Okay, so we said that the position was given by x is equal to a cos omega t plus phi. So this point here is going to be when t is equal to 0. So this has magnitude a cos phi. Our equation for the velocity is equal to minus a omega sine omega t plus phi. And our expression for the acceleration is minus a omega squared cos omega t plus phi, which is equal to minus omega squared x. So you can see immediately the relationship between x and a. We've got a negative sign here, so any number which is positive up here will be negative down here. When we're 0 up here, will be 0 down here. So that's the relationship between those two. Between these two, we're going from a cos function to a sine function. There's also this omega, which is going to change the amplitude of our function. But as you can see, when cos is at its maximum, we know that sine is 0. When cos is 0, sine is plus or minus 1. So this will have its maximum and minimum values when the cos function, the displacement function, is at 0. You need to know the relationship between these curves. Okay, so omega, we said that it satisfied the equation minus k on m is equal to x is equal to minus omega squared x. So we've already shown that omega is root k on m. Now what we want to do is work out the relationship between omega and the period of the motion. Well, the time between two maximums is one period. When we travel from one maximum point to another maximum point, it takes a time t. The maximum positions occur when cos omega t plus phi is equal to 1. So the first maximum we can say is when omega t plus phi is equal to 0, because that satisfies this equation here. Now the following maximum will occur 2 pi radians later. So it will occur when little t has plus big T plus 1 period. So our time is replaced with little t plus big T plus phi, and this is 2 pi radians later, so it equals pi, 2 pi. So now we just need to solve these simultaneously. So we've got omega t plus phi is equal to 0, and omega t plus big T plus phi is equal to 2 pi. Let's call this one 1, this one 2. Let's go 2 minus 1. The omega t's cancel out, and we end up with omega capital T. The phi's cancel each other out, and we end up with 2 pi. So we can see that t is equal to 2 pi over omega. So that's our relationship between the period and omega, or omega is equal to 2 pi over t. Now, as you know, the period is the inverse of the frequency. So we could also write omega is equal to 2 pi f. Okay, now we can also write this, because we've now got our omega is equal to 2 pi f, but we've said omega is equal to root k on m. So if the omega is on the bottom, we've got t is equal to 2 pi root m on k, and f is equal to 1 over 2 pi root k on m. So this equation actually appears on your formula sheet. Now, to practice using it, you should practice homework set 5. For Phys 1121, try questions 7 and 9. For 1131, have a go at 8, 10, 11 and 15. Okay, a quick quiz. An object of mass m is hung from a spring and set to oscillate. The period of the oscillation is measured and recorded as t. The object of mass m is removed and replaced with an object of mass 2m. When this object is set into oscillation, what will be the period of the motion? We've said t is equal to 2 pi root m on k. So now if we replace m with 2m, our new period is equal to 2 pi root 2m on k, which is equal to root 2 times the old period. So root 2 times t is the answer to that quiz question. Next question. A 0.500 kilogram object attached to a spring with a force constant 8 newtons per meter vibrates in simple harmonic motion with an amplitude of 10 centimeters. Calculate the maximum value of its speed and acceleration. And then when the object is 6 centimeters from its equilibrium position, calculate c, the speed, and d, the acceleration. And then e, calculate the time interval required for the object to move from x equals 0 to x equals 8 centimeters. Okay, let's make a record of everything we were told. We were told that the spring constant was 8.00 newtons per meter. We were told that the amplitude was 10.0 centimeters. And we were told that the mass is equal to 0.500 kilograms. Now, part A, we were asked what's the maximum velocity equal to. Now we've seen that x is equal to a cos omega t plus phi, and that v is equal to minus a omega sine omega t plus phi. Now this is going to have its maximum value when sine omega t plus phi is equal to -1. So our maximum value for V is going to be A omega. So we need to know what omega is. Now we said omega squared is equal to K on M. So that's 8.00 over 0.5, which is 16. So omega squared 16, so omega is equal to 4.00. Okay, so our maximum acceleration is the amplitude, 10 centimeters, 0.1 meters times the 4.00. So that's equal to 0.400 meters per second. Okay, part B, we were asked what's the maximum acceleration. Well, we've seen that acceleration is equal to minus omega squared x. So this will be maximum when x is maximum, and the maximum displacement is the amplitude. So A max is equal to minus omega squared A, which is minus 4 squared, which is 16, times the amplitude, which is 0.100 meters. So this is equal to minus 1.60 meters per second. So that's towards equilibrium position. Now part C. We were told it's now x is equal to 6.00 centimeters from equilibrium. And we were asked what's its speed. Now, one way to do this is to work out at what time it's at 6 centimeters and then use our velocity equation with the time to work out what the velocity is at that time. So let's work out the time. So we've got 6.00 is equal to 10.00. So this is just substituting in for x. This is a cos. Now we'll assume phi equals 0. So we've got cos omega t, so that's 4t. And so solving it for t, we've got 4t is equal to the inverse cos of 6 over 10. Now, it's important to make sure that your calculator is in radians. And so solving that on the calculator, we get 4t is equal to 0.92, and so t is equal to 0.23 seconds. And then we can just substitute this into the velocity equation. So the velocity is equal to minus a omega, so minus 0.100 times omega, which is 4, sine of omega, which is 4 times 0.23 the time. Solving that, we end up with minus 0.32 meters per second. Okay, part D. We were then asked to calculate the acceleration. So the acceleration is equal to minus omega squared x. We already have x at 6 centimeters, so this is equal to minus 16 times 0.06, and solving that on the calculator, minus 0.96 meters per second. And finally, part E, it asks us what's the time does it take to travel between 0 and 8 centimeters. So let's just do a quick sketch of what it looks like. Here's our time, here's our position. We've got the equation x is equal to a cos omega t, and we've set phi to 0. So initially it starts at amplitude a when t is equal to 0, and then it travels like this. And this is 10 centimeters. So we need to find out how long it takes to get from 8 to 0. So we're looking for this time interval here, which is the same as going from 0 to 8, which is this time interval here. Okay, so let's work out this time here, the time at which it's at 8 centimeters. So just substituting in here, we've got 8 is equal to 10 cos. Now omega t, omega is 4t. So we just solve this like we did down here, making sure the calculator's in radians. So we've got 4t is the inverse cos of 8 over 10. So that gives us t is equal to 0.1608. Okay, so 0.1608 seconds. And now we need to find this second time here when it's at 0. So we've got 0 is equal to 10 cos 4t. Now, cos is equal to 0 when this angle in here is equal to pi on 2. So we've got 4t is equal to pi on 2. So t is equal to pi on 8, which is approximately equal to 0.3927. So this is t is equal to 0.3927. So the time interval here is equal to 0.3927 minus 0.1608. Solving that, we get 0.232 seconds to 3 significant figures. Okay, now we're going to consider energy. For now, we're going to assume that energy is conserved. There are no non-conservative forces doing work, so there's no friction or air resistance acting. The energy is going to be converted between potential energy and kinetic energy, but the total energy should remain constant, as we're not losing any of it. Okay, so we know that kinetic energy is equal to a half mv squared, and we've shown that v is equal to omega a sine omega t plus phi. So just substituting that expression in for v, we end up with this expression for our kinetic energy. And the potential energy stored in the spring is given by a half kx squared, which is a half k a squared cos squared omega t plus phi. This is just substituting in for our x. Okay, so to get the total energy, we just need to sum the kinetic energy and the potential energy. We can take a squared out as a common factor, and then we can make the substitution omega squared is equal to k on m. So substituting that in, we end up with this expression. We can pull k out the front, and you know that sine squared theta plus cos squared theta is equal to 1. So replacing this sine squared omega t plus phi plus cos squared omega t plus phi with 1, we end up with the total energy is a half ka squared. Now you can practice using this equation for the total energy and relating it to the kinetic energy and the potential energy in homework set 5, for 1121 questions 10 and 11, for 1131 questions 12, 13 and 14. Okay, these graphs show you the relationship between the potential energy and the kinetic energy. For this one, we've got the energy versus time graph. So when the kinetic energy is minimum, the potential energy is maximum. And you can see they're just inverting there. With this graph, we've got the displacement versus the form of energy. Now, when it's at its equilibrium position, it's got its maximum velocity, and so it's got its maximum kinetic energy. At the two ends of the motion, its displacement is equal to the amplitude. It's just starting to change direction, so its velocity there is 0. And so it's got no kinetic energy, and all its energy is stored as potential energy in the spring. So this is just another way of showing you that information. When it's at its maximum displacement, all the energy is stored as potential energy. When it's at its equilibrium position, it has its maximum velocity, but it hasn't stored any energy in the spring, and so it's got maximum kinetic energy, and so on. Now we can use this to work out the velocity given the position. We've got that the total energy is a half ka squared, and that's equal to the kinetic energy, a half mv squared, plus the potential energy, a half kx squared. So solving this, we can cancel out all the halves as a common factor, and we end up with mv squared is equal to k, it's a common factor between these two, a squared minus x squared, and so dividing through by m and taking the square root, the velocity is equal to plus or minus k on m, a squared minus x squared. K on m is just omega squared, so pulling omega out the front, we've got the velocity is equal to plus or minus omega a squared minus x squared. Now this actually makes it much easier to solve some problems. Let's just have a quick look at the last problem we solved. Part C here, to work out the velocity, we had to start by working out the time, which was quite tedious. Another way to do it is to use the expression that we've just derived, that the velocity is equal to omega root, well, if there's a plus or minus, a squared minus x squared. Okay, so we've got plus or minus omega, which was 4. The amplitude was 0.100 squared. We were told that x, it was 6 centimeters from the equilibrium, so that's 0.06 squared. Solving this on the calculator, we end up with plus or minus 0.32 meters per second, which is what we got here. So that's a faster way of doing it. Okay, so that's all the new material. Now we're going to look at some problems that we can solve with these equations. Okay, so an object spring system moves with simple harmonic motion and has an amplitude A. When the kinetic energy of the object equals twice the potential energy stored in the spring, what is the position x of the object? Okay, so we're told that kinetic energy is twice the potential energy. Now the total energy is equal to k plus u. Substituting in, we've got this is equal to 2u plus u, which is equal to 3u. Now we know that the total energy is a half ka squared, and that the potential energy is a half kx squared. So now we're trying to work out what x is. We can cancel out the halves and the k's, and we have x squared is equal to a squared over 3. So x is equal to plus or minus a over root 3. And that's the answer to this problem, because we're not given the amplitude, we can't give a number, but whenever the position is equal to plus or minus the amplitude over root 3. Next question. A 420 gram object is attached to a spring and executes simple harmonic motion with a period of 0.250 seconds. If the total energy of the system is 5.83 joules, find A, the maximum speed of the object, B, the force constant of the spring, and C, the amplitude of the motion. Okay, so we were told it was 420 grams, which is 0.420 kilograms. It has a period of 0.250 seconds, and the total energy is equal to 5.83 joules. Part A asked us what's the maximum velocity. That will be when all the energy is stored as kinetic energy. So it'll happen when we have 5.83 is equal to a half mv squared. M is 0.420 and v max squared is what we're trying to find. So just rearranging this, 5.83 times 2 divided by 4.20 gives us v squared is equal to 27.76, so the maximum velocity is equal to the square root of this, which is 5.26 meters per second. Part B. This asks us to find the force constant, K, for the spring. Now, we know that omega squared is equal to K on M, and that omega is equal to 2 pi over T, and we have T. So we know that omega is equal to 2 pi over 0.250, so that is going to give us 8 pi. Okay, so K will equal omega squared M, which will be 64 pi squared times 0.420. Solving that on the calculator, we end up with 265 newtons per meter. Now, the last part, part C, we were asked to find the amplitude of the motion. Now, we know that the total energy is equal to a half ka squared. We now have k and we have the total energy. So 5.83 is equal to a half times 265 times a squared. So solving this, we end up with a squared is equal to 0.044, which tells us that a is equal to 0.210 meters. We only take the positive square root, as amplitudes are always positive. Next question. A ball drop from a height of 4 meters makes an elastic collision with the ground. Assuming no mechanical energy is lost due to air resistance, A, show that the ensuing motion is periodic, and B, determine the period of the motion. C, is this motion simple harmonic? Explain. Okay, so periodic motion It's just motion that returns to the same state regularly. One way to show that this is periodic is to plot a graph. So let's plot a height versus time graph. Now it starts at height 4, drops down to the ground, has a completely elastic collision, so no kinetic energy is lost. So it goes up and its kinetic energy gets converted to potential energy, at which point it has no velocity and it turns around and starts accelerating downwards again. So we're going to have a graph like this. So as the graph repeats itself, this is regular, periodic motion. So that's part A. Part B asks us to calculate the period t. So this is the period t here. Now it starts from 4 meters. Now the acceleration acting on it is just the acceleration due to gravity. So we can work out how long it takes to go down to the ground. It then takes an equal amount of time to come up again. So let's work out this. This is half a period. So we can use the equation y is equal to a half ay t squared. And so y is 4.00, it's dropping 4 meters, and that's equal to a half times 9.8 times t squared. Okay, we should probably have a negative there as it's accelerating downwards and a minus 4 there as it's moving downwards, but those will cancel out. Okay, so solving this, we have t squared is equal to 4 times 2 over 9.8, which is 0.816. So t is equal to 0.904 seconds. So the period is 2 times this. So 2 times 0.904 seconds, which is 1.81 seconds. So 3 significant figures is this period here. Okay, part C says, is this simple harmonic motion? Well, no, it's not. The acceleration is constant. It's always the acceleration is always downwards at 9.8 meters per second. It's not always directed towards the equilibrium position. So no, as the force is not always directed towards the equilibrium position. Okay, and the final question. We had a demonstration of part B in lectures. A block of mass M is connected to 2 springs of force constants K1 and K2. This can be done in 2 ways. In part A, they're connected to each other with the mass on the end. In part B, the mass is connected between the 2 springs. And we're allowed to ignore friction in both these cases. When the mass is displaced from its equilibrium, it exhibits simple harmonic motion. Derive an expression for the period in both cases. Okay, so for case A, at equilibrium, we've got our mass M, we've got K1, we've got K2, we can call this length 1, we can call this length 2, and they're not stretched. Now we stretch the string by applying some force. We have it stretched some distance x, and we've got L1 plus x1 is the length of this first spring, L2 plus x2 is the length of this second spring, x1 plus x2 is equal to x, the total extension of the spring. So if this is 0, there's 0, then this is x, a position x from there. Okay, now the tricky part of this question is to realise that these 2 springs are applying a force on each other. And Newton's third law tells us that as they're connected, this force must be opposite and equal. So we can say The force applied by this spring is equal to K1x1, and that must be equal to the force of this spring, which is K2x2. So we have K1x1 is equal to K2x2. So we can write x2 is equal to K1 on K2 x1. Okay, now we've got that x, the total displacement, is x1 plus x2, and we can write this as x1 plus K1 on K2 x1, just substituting in from here. So this is equal to 1 plus K1 on K2 x1. So x1 is equal to x over 1 plus K1 on K2, multiply the top and the bottom by K2, and we end up with K2x over K2 plus K1. Now let's just consider force 1. So we have some total force here. Total force is going to be pushing this back here and will be equal to minus Kx. But the force on spring 1, F1, will equal minus K1 times the extension of this first spring, X1. So this will be equal to minus K1 times X1, which is K2 x over K2 plus K1. And so the force will be minus K1 K2 over K1 plus K2 x. Okay, so this here is our effective spring constant for this system. And we've derived the equation that the period is equal to 2 pi root m on k. In this case, it's the effective k. And so this is equal to 2 pi root m. Now k effective is K1 plus K2 over K1 K2. And so that there is the period for this system. Now case B is a little bit easier. Here's K1, here's K2. They've got length L1 and L2. Then we disturb it. This is in equilibrium. Now we disturb it. We pull at a distance x. We've still got K1, K2. And this length is now L1 minus x, and this length is L2 plus x. Okay, so let's consider the force. Due to the first spring, it's acting to the right as the spring's been moved, the mass has been moved to the left. So it's K1x. In the second case, the spring's been extended, so the force is to move it back to its equilibrium position, which is again to the right. So we've got the force K2x. And so our total force F is equal to K1x minus K2x. This is minus, they're both back towards the equilibrium position. We put our minuses there to show that they're towards the equilibrium position. So this is equal to minus K1 plus K2x. So this is our effective K. And so our period is equal to 2 pi root m over K effective, which is K1 plus K2. Okay, so that's the end of that lecture.